This video is part of the Passport.js user authentication series. I've linked in the description the playlist that you can peruse to see the videos in order. That said, this video can also stand alone as just a basic crash course in public key cryptography. This is a widespread topic. Public key cryptography and cryptography in general can be used for several different things, whether you're talking about user authentication, cryptocurrency, or even just secure transport over HTTPS. So I'm going to, in this video, be talking about what is public key cryptography and how does it work from both a conceptual and practical level. So we're going to walk through the basics of conceptually how it works, but we're also going to look at some code and see it in action. Before I get into what public key cryptography is, we need to distinguish between two terms. So that would be asymmetric and symmetric cryptography. So public key cryptography, what you see on the screen, is a form of asymmetric cryptography because you have a public and a private key associated with it. Now, a more basic form, in what is used for TLS, or Transport Secure Layer, or whatever, I think that's what it is. Otherwise, the protocol that we use to transport data securely over an insecure internet channel, that is going to be symmetric cryptography and is identified by a single key. So a great way to think about this is maybe in a classroom setting. So say you're sitting in a classroom and you want to pass a secure note to one of your friends across the room, but you want to make sure that if the teacher intercepts that message, they can't read it. So what you would do is before class, you're going to connect with your friend or friends that will be basically interchanging notes, and you need to come up with a secret key. So you might just come up with a real simple secret key, and that key is going to be, okay, we're going to take every letter in the message and we're going to increment it by 2. So an A becomes a C. And then to decrypt it, you just have to take that C and bring it down 2 letters to be an A. So now that the people that are interchanging messages know what the secret key or the cipher algorithm is, they can easily read what the teacher thinks is gibberish when the notes are passed. So to encrypt the data, one student is going to basically write something down, write the message that they want, and then they're going to transpose it using the cipher algorithm. So once again, an A becomes a C, a B becomes a D, and so forth. Then they'll have someone walk that note across the class or pass it from desk to desk, and we'll say that the teacher intercepts it. The teacher cannot figure out what the note says, it just looks like gibberish, but the student on the other end could have decrypted that message by using that secret cipher. So that is what we call symmetric cryptography, and obviously we need to protect that secret. Now this is again used in transporting messages over the internet. It's also used a lot in web application development. You'll commonly see something called a secret key, and that is what you'll be using to encrypt some sort of data. Now on the other side of things, we have public key or asymmetric cryptography, which is a little bit more complicated and involves a private and a public key pair. So these private and public key pairs are mathematically linked, as we'll see a little bit later in this video, but the basic gist of it is if you have a public key, you can give this to anyone as long as you keep the private key secret, and then we can do 2 things with that public-private key pair. The first use case is going to be exactly what we just talked about with encrypting some sort of data. So you might think of this, the way that I like to think of it is a padlock and a key. So basically, I mean, this is kind of a contrived example, but basically think about maybe we're sitting in that same classroom and we have some sort of lockbox. And so one student is going to write a note, which is just going to be in plain text, and they're going to put the note in the lockbox. So what they'll do now is they will close the lockbox and lock it with a padlock. So that padlock before class was actually given to this student by another student who actually owns the key to the padlock. So just to level set here, the student that's writing the message has the public key of the other student who will eventually receive that message and decrypt it with the private key that corresponds to that public key. So in other words, student writes the message, puts it in the box, locks it with the other student's public key. Then we send the box across the room. We'll say the teacher intercepts it, tries to open it, but of course they don't have the private key that corresponds to that padlock or just the physical key that will unlock it. So they can't unlock it, can't see the message. But if it gets to the student who does have that private key, they can just unlock the padlock, open the box, and see the message. So that is your first use case. Now the second use case is a little more complicated, and we're not going to be able to understand it in the form of the classroom setting. We're going to have to get into a little bit more complicated math. But that second use case is called a digital signature or identity verification. And this comes in handy when we're talking about user authentication and is pretty much the entire reason for me making this video. So again, if you're following along the Passport.js user authentication series, what you're going to want to really focus on in this video is that second use case or identity verification. As you'll see, to use these two use cases, all we're going to do is change which key we are encrypting and decrypting with. So to encrypt some sort of data but not protect an identity, we're going to encrypt with the public key and decrypt with the private key, as with the padlock and key in the classroom. Now the second use case, we're just going to flip that. We're going to encrypt with the private key and decrypt with the public key. Now, in order to understand this, we have to understand what a trapdoor function is, and this comes in several different forms, but in the case of public key cryptography or asymmetric cryptography, we're talking about elliptic curve multiplication. We'll get to that in 1 second, but first let's just generally understand what a trapdoor function is. So basically what a trapdoor function is a one-way function that takes some pretty big piece of data and compresses it into a deterministic small piece of data outcome. So in other words, we can have an infinitely large piece of data. We could have, let's say, something as simple as what you see on the screen right now, or we could have something as big as maybe an entire book. And what we can do is we can take that infinitely large or small data and put it through what we call a trapdoor function. In this case, we're using a SHA-256 hash function, and that will always create a deterministic outcome. So it's going to be the same length. I think it's I don't remember off the top of my head exactly how many bytes this is, but it's a hexadecimal representation of the data on the left. So if we were to come to an online SHA-256 hash calculator, I've pasted in that exact value in JSON string form, and we get out this hash value. And so anytime we put this particular data into this SHA-256 hash function, we're going to get the same exact output every single time. So it is deterministic. You can try it for yourself. Now, we also have to know about this that we cannot go backwards. So from this data on the right, there's no possible way that we can derive what the original data was in the first place. Even though we know that we're using the SHA-256 hash function, we know that that's only one way. You can't go the other way. The last important thing to recognize about this is we have an infinite number space, essentially. Now, it's obviously not actually infinite, but there are so many different combinations that the SHA-256 hash function can produce that the chances of us having two different pieces of data that come to the same hash value is essentially impossible. Now, there's plenty of Stack Overflow questions on this, and you can read up on them on your own time, but basically the probability of this guarantees that we're always going to get a unique hash value. What we're interested in when it comes to public key cryptography or asymmetric cryptography is a one-way function or trapdoor function called elliptic curve multiplication. Now, it's not actually multiplication, it's a cryptographic function, and basically all we need to know about this is that it mathematically links the private and public key. So in other words, using the private key, we can derive the public key, but having the public key, we can never get back to that private key. So in other words, we can share the public key with anyone in the world, and they'll never be able to figure out what private key corresponds to that public key. This, again, is useful for those two use cases of either protecting some sort of data or verifying an identity. We'll see a little bit more how this works when we actually get into the code, but first let's kind of take a quick glance at how elliptic curve multiplication works. So on the right, you'll see the elliptic curve graph, which is useful to us because given any point on on this graph, we can take the tangent of that point and get to another point on the graph. So say we're right here on the graph. Well, this curve extends infinitely, so we can just take the tangent all the way up to that curve. So let's go to the next slide and first start out with what we call the generator point. Now, the generator point is an arbitrary random value or coordinate that we will always start with. Now, this point in many cases is going to be a fixed point that we use for a large private key, I guess you could say number space. So we always start with the same generator point, but then the variable in the equation is the private key, and we take that private key and we multiply the generator point by the value of the private key. So again, the private key is some infinitely, well, not infinitely, but it's some small or large value, and so we can, just like we can take g times 2 and g times 3, we can also do g times 10 trillion or whatever the total value of that private key is. Now you might ask, how are we going to multiply g? That doesn't make any sense. This is a graph, and how are we going to actually do multiplication? Well, the way that works in elliptic curve multiplication is by drawing tangents, as we talked about. So you start with the generator point and say that your private key's value is 2. Now, obviously, it's never going to be 2. It's going to be a much, much larger number, and we're going to do this process many more times. But essentially what's happening is we start with g, we draw the tangent to that point on the curve, which the tangent intersects this other point on the curve. Then from that other point, we say, okay, what is the opposite side of the curve? So we draw this completely vertical dotted line to get to this last point on the curve. And that is essentially the multiplication value of our operation. So g times 2 is going to equal this coordinate down here at the bottom. So you can see how this is kind of, it's not exactly the multiplication that we're used to, But essentially what is happening is we start with this arbitrary generator point, we multiply or we go through this process however many times the public or the private key value is, and eventually we will reach a certain point on the elliptic curve, and that is going to represent our public key. Now, we cannot get back to the private key based on the public key coordinate, but what we can do is we can derive that the private key that maybe signed a message corresponds to the public key. So in other words, what you need to understand is that using the complex math that elliptic curve cryptography does, we can actually verify that a public key corresponds to a given private key mathematically without revealing the private key to the person trying to verify it. So in other words, we can decrypt a message using a public key. You'll see how this applies a little bit later in the video. Just to recap before we get into the actual code, if we want to do data encryption, we're going to encrypt with the public key and decrypt with the private key. If we want to do identity verification or a digital signature, we are going to take the message that we want to sign and we are going to essentially sign it with our private key, and then some random party, some receiver of the message is going to have somewhere the public key that corresponds to the private key, and using that public key, as we just talked about, we can use that elliptic curve algorithm to verify that yes, indeed, the person who signed it has the private key that corresponds to that public key. Okay, so let's take a look at the actual code that will create this private and public key pair. Now, there's of course command line utilities that you can use to do this, but I wanted to kind of write it out so that we can explain it and understand it a little bit better. Let's go to VS Code real quick and create a new file. We're just going to call this create keypair.js. We'll open up this file and I'm going to paste in some code that I already wrote. So let's walk through this code really quick. We're using the built-in Node.js crypto library and then the built-in Node.js file system so that we can output the keys in this directory. And you'll see what's happening is we have a single function that will generate a key pair. All it's doing is using the crypto library to generate the private and public key using that elliptic curve multiplication under the hood. And then we're going to write that private and public key to separate .pem files in the current directory. So you'll see that here's where the magic is actually happening, and then down here is where we're taking those values and writing them to the files. So you can see that we're using the RSA algorithm to generate the keys. That's a pretty standard algorithm to use. And then these, you can just go ahead and look at them on your own if you want to pause the video to see what they represent. But basically, this is all the math that we just talked about. And when we run this script by saying node create key pair, it's going to finish, and then you'll see on the left we have both a private key and a public key. And in other words, this private key is something that we want to keep to ourselves, not share with anyone, and the public key can be shared with absolutely anyone with full confidence that they will never be able to figure out what this private key is. Alright, now that we have our private and public key, let's go ahead and use that in both of those two use cases that we talked about earlier. So to do this, just remember we have the private key and public key saved in this current working directory. So I'm going to close them. I'm going to close the create key pair, and then I'm going to create a new file called encrypt.js. And in this new file, we're going to write an encryption formula where we take some sort of data and we encrypt the data and we protect that data. So I'll paste in the code. You're going to see we require the crypto library again, and then I've got a single function that's going to take a public key and a message as an argument. So again, if we want to protect data but not an identity, we encrypt with the public key and decrypt with the private key. So what this file is going to do is it's going to take the message that we give it, it's going to create a node buffer with UTF-8 formatting from that message, and then it's going to pass that buffer into the built-in public key encrypt function that the node crypto library provides us with. And then what we're going to do is we're going to export this function so that we can import it into another module. So now that we have this, we can save it and then create one more file called main.js where we're going to do a lot of the work. Let's go on ahead and open up main.js and copy in some code that I already wrote a little bit earlier. So again, we're using the file system, and then we're also importing this file right here that we just wrote. So by importing this, we have access to the encrypt with public key function. And so what we're going to do in the main file is we're going to first get access to the public key that we created and stored in that PEM file in the current working directory. So we just use the file system to do that. And then what we're going to do is create an encrypted message and store it in the encrypted message variable. So you'll see that we are going to use the function that we defined in this other module. We're going to pass in the public key that we got from the file system that we created earlier. And here is our super secret message that we don't want anyone to be able to decrypt over a public channel. So once we do that, we can basically console log the encrypted message as a string, and you'll see when I save and run this file that in the terminal you'll see some gibberish that we cannot decrypt. So node main.js, and of course we see a bunch of gibberish. This means absolutely nothing to us, and there's no chance that we figure out what this super secret message was based on this data. So in other words, this right here is what you're going to transport over any sort of insecure transport layer. So to decrypt this, we can do that with our private key. So let's take a moment to see how that works. We'll clear the terminal and create another file called decrypt.js. And when we open that up, we can paste in a similar function to the encrypt file. So we're going to require the node crypto library, define a single function where we decrypt with the private key, and then all this will take is our encrypted message and the private key, and then it'll use the built-in node crypto library private decrypt function. So we're going to export this function so that we can import it in another module, save it, and then we're going to use the main module to actually decrypt this. Okay, so you're going to have to use your imagination a little bit because we're both encrypting and decrypting in the same file, but hopefully this will make a little bit of sense. So at the top part of the file, we have encrypted our super secret message right here. At the bottom part, we are going to import our private key, and then we're going to use the decrypt function, and we're passing that encrypted message into the decrypt function. And finally, we'll take that decrypted message and convert it to a string and print it to the console. So what we should expect with this file now is that in the console we're going to get that gibberish message that is encrypted, and then finally we will have the decrypted message which should say super secret message. So let's run that real quick. We'll say, gotta come down to the terminal, we'll say node main.js, and we have a problem. So let's see what the problem is. Decrypt is not defined because I did not import it. So let me import that real quick. Now that we've imported it, we can use the function try one more time. So we got the gibberish up top, and then we finally got the decrypted message at the bottom. So that is just a basic way that you can understand how we use private and public key pairs to protect data over an insecure transport layer. In order to see how digital signatures work, we're going to have to add a few things to our encrypt and decrypt modules. Because remember, we are going to encrypt and decrypt with different keys based on which use case we want to use. So let me do in the encrypt function or module, I'm going to add another function called encrypt with private key. So we can encrypt with the public key in case of data protection, or we can encrypt with private key in case of a digital signature. So let's go ahead and export that from this module real quick. So encrypt with private key. So now we have a module called encrypt, which we can do both encryption with the private or the public key. Likewise, we need to do this in the decrypt module. So let me just highlight this whole part, paste it in. We've got an extra import here, and we've got our function decrypt with public key. So now that we have those components, we can see how a digital signature actually works. But mind you, a digital signature is a little bit different than protecting data. We're going to have to go through just a little bit extra work to do this. Because this is a little bit more complicated, I'm actually going to make separate files for the steps of the process. So with the digital signature, we have some sort of data that we want to put our signature on. So just think of it like a legal document. You have the document itself with the data, and you want to sign it. And you want to make sure that the receiver of that data is assured that both the data that was on the document has not been tampered with. We don't want someone intercepting it and changing some of the legal proceedings on that paper. And we also want to make sure that the person we think signed it actually did sign it. So that's step one. We need to sign the message. Step two is actually verifying it as I just described. So for step one, let me go ahead and close all of these files. You know what is in them. So we will create a sign message.js file. And in this file, let's go ahead and import some different modules. So let me walk you through what's actually happening here. Starting from the top, we have the node crypto library, pretty familiar. We also have the file system, and then we have the encrypt and decrypt modules that we created ourselves. Now the last thing is this hash function. And this is a SHA-256 hash. We talked about this a little bit earlier, and it is a trapdoor function that takes a pretty much infinitely large or small piece of data, and you put that data through the hash function, and the output of that hash function is going to be every single time you do it, it's going to be the same exact value. And that value is going to be small enough that we can kind of transport to different places. It's always going to be 64 characters long, which each character is 4 bits, so you have 256 bit value that is always going to come out of that function, no matter how big or small the data you put into it. Finally, at the bottom, you'll see that I have a piece of data. This is going to be the data that we are going to sign. Now, you'll see that I've got my first and last name, and then in the social security number field, we're never going to put that because remember, this second use case of signing some sort of data does not protect the data itself. If someone intercepted this data on an insecure channel, they would be able to read everything that is contained in it. So we never want to put any sort of confidential information in data that we are digitally signing. Alright, so the first thing that we need to do is we need to take this data right here, since it's pretty large, and we need to compress it down into that SHA-256 hash. So to do that, deleted it. To do that, I'm going to paste in some code that I wrote earlier. And what this code is going to do is first store the JSON string value of this data right here. And it's going to store that in a variable. And what we're going to do is we're going to use that node crypto library hash function, and we're going to hash the data that I just put in string form. Then we're going to convert that into hexadecimal format. And this is important because the format that we're passing values between function in is actually really important when we're using the crypto library. We are now ready to actually sign this data. So let's paste in some more code. First, we're going to get access to the private key that we created earlier. And second, we are going to store the signed message in a variable. We're going to use the encrypt with private key function that we created using the node built-in crypto library. We're going to pass in the sender private key. So in this case, I am the sender of this data, and I own a private key that I'm going to sign this message with. So I will sign the data with my private key, and this data is going to be in the form of the hashed data. So we're not just going to sign this big data object, we're going to sign the hashed version of that data. Now the last thing that we have to do is kind of that extra step that I was talking about. So if you just sent this signed message to someone, they're not going to be able to do anything with it. Not only do we have to verify that nobody has tampered with our legal document, so to speak, we also need to verify that the person that says they signed it actually did sign it. To do that, we need to provide the receiver of this data with a few additional pieces of information. So those pieces of information is number one, which hash function we used to hash the data. Number two, we have to actually give them the original data so that they can take the hash function, take the hash of it, and then they can eventually take the signature that we provide them with and match it up with that hash data to make sure that I actually signed the data in the first place. So let's go ahead and see what that looks like. We'll go ahead and create a final piece of data. So we'll say package of data to send, to be very explicit, and we'll paste in this data object. So we've got an algorithm. So this tells the receiver of data, I want you to use the SHA-256 algorithm. And what I want you to put in that algorithm is the original data that we created. So you'll see that the original data is my data, which is the original object of data that we will use. And then, of course, we have the signed and encrypted data, which we assign to the signed message right here. So with this information, a receiver of this data can verify using my public key that not only was the data not tampered with, but I also signed it. Last, let's go ahead and export this package of data. So module.exports.data, or let's just call it the same thing that we called it here. Package of data to send equals package of data to send. So we can access this from another file. To do this, we're going to create another file called verifyidentity.js. We'll open up that file and we'll put our imports in there. So we need the crypto library, we need that decrypt module that we had created on our own, and then we need to import the data that we just exported from that other module. So this is everything that we need to verify this message. Now we also need to bring in the public key of the sender. So this will be made publicly available, and we'll say that, you know, I sent this data in the first place, but my friend Jim, whatever, is going to be verifying it. So Jim will need my public key to do this, which again, public key is public and anyone can see it. You can feel confident that they're never going to be able to figure out what the private key was. And one thing you'll notice that I required this in, but I need to grab the variable that we exported. So require this module and the variable. So our received data is equal to this object right here in the signed message file. Next, we need to actually take our own hash of the data that we were provided. So to do that, we know that we're using the SHA-256 hash, and so we can use that hash function to hash the original data. I'll paste this in here, and you'll see that our hash function is going to be the built-in node hash function, and it's going to be the algorithm that was in that data package. So I know this is a little confusing, but this line right here in the verify identity file is the same as this import right up here. So where we said create hash SHA-256, we're also creating a hash, and we're just using that algorithm that we received in the data package. Like I said, we also need the public key of the sender, so we'll go ahead and get that in the public key variable. The next step to doing this is we have to take that data that was signed and decrypt it. So let's think about what this is actually doing. I'm going to paste in the code, and we're going to use our decrypt module. We're going to pass in the public key right here. This is the public key of the sender. And then we're going to take the data that we received, and we're going to pass in the signed and encrypted data. So if we come over back to the signed message, let's figure out what this was. So our signed and encrypted data was our signed message, which basically, if we decrypt that message, what it's going to give us is the hash value that we derived from this original data. So what we're going to get in this variable right here, the decrypted message, is simply a hash value. So in order to verify that, we can then take our own hash of the data that was provided in this object right here. So this is the original data, and if we take a hash of that and compare it to the decrypted message here, they should match. And if they do match, we can know that not only was the data not tampered with, but it was also signed by the person who said that they signed it. One extra step we've got to do is we've got to turn that decrypted message into a string value to pass it into our function. That's just a formatting thing. Finally, we say we want to look at the hash of the original. So we're going to actually take the hash of the data that was passed to us in that data package, and then we're going to turn that into a hex value. To verify it, we'll just do a basic if-then statement. So we'll say if the hash of original hex, so basically our own, so this is the receiver of data, Jim, is doing this. He's taking a hash using the designated hash formula and just turning it into a hexadecimal value so that we are comparing apples to apples. And then we're taking the decrypted message hex, which is basically what came with that, is what we decrypted, in comparing them. So if it is the same, then we're going to say success, the data has not been tampered with, and the sender is valid. So let's see if this works. Let's go down to our console and run node verify identity. And you'll see that it says success, data hasn't been tampered with, we have the right sender. So hopefully that makes sense. That is the second use case of public key or asymmetric cryptography, and is called a digital signature. It's a very common way to verify data and identities, and you'll see if you are following the Passport.js series that this video is kind of associated with, you'll see exactly how that works when we actually are authenticating users. Now, just as a consolation for this video, what we just did over the last few minutes when we were signing and verifying a message is the same exact process that is used with JSON web tokens. So you might say, wait a second, there might be a better way to transport this package of data over the internet. And you are right, there is indeed a better way to do this. If we were to send this package of data, it's going to actually be a pretty large piece of data, and it's going to slow all of our web searches down, especially if we're using it for some sort of authentication. So naturally, the easier way to do this is to represent this piece of data in a much smaller form. Just like we took the original data and we took a hash of it to make it smaller and more transportable, we can also do that with the data package that is sent to the receiver of data and is used to verify the original data. Let's jump into the browser real quick. And what I have pulled up is JWT.io, which has a really simple JWT visualizer per se. Now, don't focus on what is going on here because I have a separate video on that, but just recognize the structure of what's going on. So on the left, this is our entire JWT token. And you can see that it is pretty short, and it would be very easy to transport over the internet in a quick and efficient manner. But if we decode this JWT, it has the same critical information that we saw when we were signing and verifying an identity in our code earlier. So first we have the algorithm, which is represented by this red string. And so this will tell us exactly what SHA-256 hash algorithm that we have to use to decrypt the data. Then we also have a payload, which is represented by this purple string. And you can see, I guess I deleted something here, but you can see that it has all of the information that we would need to include in that payload of data. So this, you could consider that legal document that we are signing. And then finally, at the bottom, you have the actual signature, and this signature is going to include, you'll see the public and private key here, but this is actually just going to be the signature that we wrote in the code earlier, and we can verify it with a public key. Talking about JWTs is just kind of a bit of extra information. You don't need to truly understand JWTs to understand public key cryptography, but I kind of just wanted to foreshadow if you are watching the Passport.js user authentication series. If you enjoyed this video, found it helpful, be sure to give me a like and subscribe. And if you're continuing on to the Passport.js user authentication series, we will be talking a little bit more about JWTs in another video.